Welcome to Math TV with Professor V. In this video, we're going to look at evaluating integrals using integration by parts. And this is a continuation video to the video lecture, which I'll link right here on integration by parts. So if you haven't watched that already, or if you need a little bit more of an intro, providing some context into integration by parts, be sure to check it out first. All right, so just as a quick recap, when we apply integration by parts, our original integral needs to be of the form u times dv. And then after applying the process, we end up evaluating a different integral, and the result is equal to u times v minus integral of v du. And think of it this way. Here's your original integral. You need to choose or identify what u are, or what u is, and what dv is, okay? What those both are. Then, from there, you have to find what du is and what v is. Notice right here, what you end up integrating is v times du. So you have to keep that in mind, that this product right here, v du, is what you're going to end up integrating after you choose u and dv. So make sure you do it in such a manner that this product is as simple as possible to integrate. So I'm just going to write a little reminder. We want this product, that's really the key, to be as simple as possible to integrate. Okay, and then kind of think like whatever you don't want to deal with, usually that ends up being u, because see how we don't end up integrating u? There's no u here, just du. All right, that's going to motivate a lot of this discussion. Another thing that could help you when you're trying to decide what should I let u equal, and I mentioned it in the other video, but let's just rewrite it here. So if you're going to choose u, you can remember the acronym LIPET, or LIPET if you want to put a little accent on it, whatever, you do you. And what it stands for is, typically, if you see a log, natural log, you would let that be u. If you see some sort of inverse, like a trig inverse function, then if you see a polynomial, if you see an exponential function, or if you see a trig function. So, and there is like a ranking to it, okay? So typically if you see logs, you would let that be u first. Okay, you ready for some examples? We're just gonna crank through a few. Here we go. First one, evaluate the integral. We have integral of natural log of x over x cubed, dx. So let's go ahead. First select what u and dv should be. And I'm going to let u be natural log of x, all right? Also, antiderivative of natural log of x is not one that we can very easily compute. I mean, you have to do integration by parts, and so you can memorize it, but typically we want to take a derivative of natural log of x. Its antiderivative is not super user-friendly. So if u is natural log of x, then what's left over? Dx over x cubed. That's going to be my dv. So dx over x cubed, or that's the same as x to the negative third dx, right? Good. Now from here, we need to find du and v. So du is going to be the derivative of natural log of x, which would be 1 over x. Don't forget that dx. And then to get v, we're going to integrate x to the negative third, anti-differentiate it. So add 1 to the exponent, it's going to become x to the negative second, and then divide by the new exponent. So I'm just going to put a negative 1/2 in the front, and we have x to the negative second. Okay, check. Is this product down here, v du, would you be able to integrate that? Yeah, no problem. Because 1 over x, I could rewrite that as x to the negative first. When I multiply it by x to the negative second, we got this under control. And then remember, what goes outside the integral in the front is uv. And now we don't have to deal with that natural log anymore. Hooray. Okay, so here we go. So the formula is uv minus integral v du. Here's uv, u times v. Negative 1/2 x to the negative second natural log of x minus v du. But do you see how v already has a minus sign? So I'm going to switch this, make it plus. And then I always like to put my constants outside of the integral. So that 1/2 is also going to go outside. That way I can just focus on the function that I'm anti-differentiating. And we have 1 over x times x to the negative second dx. Looks good. Okay, so let's start rewriting things. We've got here negative 1/2 x to the negative second natural log of x plus 1/2 integral. I said earlier, but I'll remind you, 1 over x is x to the negative first. X to the negative first times x to the negative second is going to be x to the negative third. Remember, we add our exponents. Beautiful. Okay, let's keep going. So we have negative 1/2 x to the negative second natural log of x plus 1/2 times, if I integrate x to the negative third, we add 1 to the exponent, so it's going to become x to the negative second, and then divide by the new exponent, which is the same as multiplying by negative 1/2. And then don't forget your plus c. Don't forget, don't forget. Okay, everything looks good. Let's just clean it up for our final answer. So negative 1/2 x to the negative second. I can write that as negative 1 over 2x squared, right? Move that x to the negative second to the denominator. Natural log of x. Minus 1 over, we have here a 2 and a 2 and an x to the negative second. So that would be 4x squared plus c. So that's our final answer. Let's box it. Looks good, right? Okay, that was a nice little warm-up. Things are going to get more intense. Shall we move on? You're good? Fabulous. Moving on, example number 2, integral of cosine inverse of x. Okay, if you did not memorize all your derivatives and inverses from Calc 1, you're going to struggle in this section. Because remember, we know the derivative with respect to x of cosine inverse of x. Or at least we should, right? The derivative is negative 1 over rad 1 minus x squared. But that's not what they're asking us for here. We're asked for the antiderivative of cosine inverse of x dx. Oh me, oh my. And no, it does not involve a sine inverse, okay? So don't start making up some weird illegal rules. So here we're going to actually apply integration by parts. Okay, remember LIPET? Yes, okay. So pick u, pick dv. You really only have one option. Here's cosine inverse of x. It has to be u. I also comes very high up in that ranking, right? In LIPET, it's the second choice. So there's no logs. It's probably going to be cosine inverse of x. I'll show you why it can't be the other way around. dv cannot be cosine inverse of x dx because now you've done absolutely nothing. Now to find v, you're going to have to integrate cosine inverse of x dx. And isn't that what this problem's asking us to do? So that's a pointless way of setting things up, okay? Don't do that. That'll get you nowhere. All right, u is going to be cosine inverse of x. And remember, whatever u is, you don't end up integrating. So that's good. That cosine inverse of x is going to be out of our life in just a minute. And then dv is just dx. Oh, how sweet. Okay, so du then will be negative 1 over rad 1 minus x squared dx. Yes? Fabulous. If you haven't memorized that already, do so ASAP. And then v would be what? Dx is the same as 1 times dx, right? So whose derivative did you take to end up with a 1? Just plain old x. Beautiful, beautiful. All right, so we're going to have u times v. So this is x cosine inverse of x minus v du. Do you see how there's a negative here? Yes, you do. So let's switch this. This is now plus integral x over rad 1 minus x squared dx. All right, great. Now let's see here. I have to integrate x over rad 1 minus x squared. So I'm observing the fact that underneath the radical, I have a quadratic expression, 1 minus x squared. And I'm leaning towards making a substitution. Think of u substitution. Because if I let my variable be 1 minus x squared, its derivative would be negative 2x dx, which is perfect because I have an x dx in the numerator. But we have to be careful and precise. We've already used up the variables u and v earlier, right? When we set up our integration by parts. So you can't use a u substitution. Pick a different letter. Let's use t. How about that? So let's let t equal 1 minus x squared. So dt would be negative 2x dx. And what do we have sitting here in our integral? We have an x dx. All right, so I want to isolate the x dx on the right-hand side. So negative 1/2 dt is equal to x dx. How we doing? Happy, happy? Good. So rewriting what we have so far, x cosine inverse of x. I'm going to put this negative 1/2 outside my integral. All right. So minus 1/2 integral. X dx is now dt over square root of t. Very good. Do not mix variables when you're making a substitution like this. So don't have your integral involving t's and x's at the same time because you're in the process of switching and making the substitution. Okay, that's not well defined. So do it in one shot. Good. So in order to finish the problem, rad t is in the denominator. So let's rewrite it as t to the negative 1/2 power. And then we're in business. So to integrate this, you got to add 1 to the exponent, divide by the new exponent. So x cosine inverse of x, it's just coming down every single line. Rewrite it, don't be lazy. Adding 1 to negative 1/2 makes it positive 1/2. Dividing by 1/2 is the same as multiplying by 2. Very good. 2t to the 1/2. Now we put plus c right here. Good. The 2 and the 1/2 are going to cancel. Do you see that? Oh, how nice. So what's left over? We've got x cosine inverse of x minus radical. What was t? Do you remember? T was 1 minus x squared. So that's going to go here plus c. All right, very nice. So this is the antiderivative of cosine inverse of x. Remember that was the original integral? Don't memorize this one. There's really no point. Just remember how to find it, okay? Make sure you do memorize the derivative of cosine inverse of x, sine inverse of x, and tan inverse of x. Those will be essential. All right, lovely. Let us look at something a little more involved, and I'll show you tabular integration, okay? Integration by parts. So here we have x cubed times cosine of 7x dx. So think of LIPET. Okay, polynomial comes before trig function. So probably we're going to let u equal x cubed. And that makes sense because du would be 3x squared. So already dx, the degree is going down by 1, right? So then I would let dv be cosine 7x dx. And then v would be 1/7 sine 7x. However, we're going to have to integrate this expression here eventually, right? You'd have like minus 3/7 x squared sine 7x dx. And then notice you'd have to do like another integration by parts a couple more times. How many would it take? Well, enough for x cubed to basically go down to being a constant so that you're just integrating a trig function. So it's going to take a few iterations, which can be a little obnoxious in the notation, especially keeping track of the negatives. So when this happens, it's a good idea to use tabular integration by parts instead. All right, so here's how the setup is. You pick, obviously, one part of your integral that's going to be u, the other part is dv. Okay, and then you're going to set up two columns. So one of them is where you keep differentiating over and over, and the other one you keep anti-differentiating over and over. So remember, u was x cubed, and then dv had cosine 7x dx in it. So you can just write cosine 7x. So here's the process, super cool. Start with the column on the left where you're differentiating and just keep taking the derivative until you get 0. So basically you use this process when you have a polynomial, right? Okay, so x cubed, derivative of x cubed, 3x squared. Derivative of 3x squared, 6x. Derivative of 6x, 6. Derivative of 6, 0. Okay, now we keep anti-differentiating until we have the same number of entries in the second column. So I have to do it 1, 2, 3, 4 times. So antiderivative of cosine 7x is 1/7 sine 7x. Where'd the 1/7 come from? I've explained before, when you integrate, if there's just a constant in front of the variable, you can u sub, or just remember to divide by that constant, because you want to undo the chain rule from differentiating, okay? If you need a recap on that, I'll link a video here where I walk you through it, but hopefully at this point we can all keep up. All right, antiderivative of 1/7 sine 7x. It's going to have to be a negative cosine, right? Because whose derivative did we take to end up with the positive sine 7x? It was a negative cosine. And then we got to divide by 7 one more time, so this is going to be negative 1/49 cosine 7x. Good. And then anti-differentiating again, I'm going to divide by 7 once more. So 7 times 49 is 343. It's going to stay negative sine 7x. And then one last time, 343 times 7 is going to be 2,401, and this time it's positive cosine 7x, right? You have to take the derivative of a positive cosine to end up with a negative sine. Lovely. Okay, so now that you have your columns filled in, this is what you do. You're going to take products on the diagonal, just like when we did integration by parts regular way. So you're going to take this diagonal product, this diagonal product, this diagonal product, and this diagonal product. Okay, so our final answer is going to have 4 terms in it. The first product, you don't change the sign, just leave it as it is. The second product, you're going to add an extra negative. You're going to multiply it by -1. Because if you think about it, if you sat there and set up integration by parts the traditional way, you would have an extra negative to distribute through to these terms. So it just keeps alternating, plus and then minus, okay? So plus means just don't change the sign of the product of those two terms. Minus means add an extra negative. All right, and we're done. I kid you not. It was that fun. So here we go. This is going to equal x cubed times 1/7 sine x. You know how I'm going to write it? If Yeah, 1/7 in the front, you bet. X cubed sine 7x. Now check out this product. There's already a negative, and then I'm going to multiply by another negative, so it's going to be positive now. Plus, we should write 3/49, shouldn't we? Yes, 3/49, x squared cosine 7x. One more. 6 and 343 won't reduce. No, because 343 is just 7 cubed. Okay, it's negative, this one. Yes, it is. So minus 6/343x sine 7x. One more. Minus 6/2401 cosine 7x plus c. Beautiful. So try it on another problem. I think you'll like it. It's a time saver for sure. Okay, cool. Hope you found that enjoyable. I've got a few more for you. Don't you worry. Next example, integral of 5x times sine squared x. Again, LIPET to save the day. Polynomial comes before trig. Also, if you let u be sine squared x, it's not going to be good. Look, this is what people forget. Sine squared x means sine of x squared, right? I know. We put this here as an abbreviation, but sometimes students forget that it means you're squaring the whole quantity. So then du is not going to be fun. Because remember, there's this thing called the chain rule. So you have 2 sine of x to the first times cosine x dx. That already looks nasty, right? Because then if u was sine squared x, dv would have to be 5x dx. Don't write this down. This is me showing you why this setup is no good. And then v would be 5/2 x squared. And then now this is what you're integrating, and you've just made life a lot worse than what it was. Do you see that? Okay. Sometimes you just got to set them up wrong to learn the error of your ways and not make those choices again in the future. And then you'll get to a place where you'll pick correctly every single time. I'm going to erase this, but my suggestion to you as a student is leave your wrong work. That way, just put an X through it so you know what went wrong and why not to do it again in the future. No shame in that. Okay, I'm going to let u be 5x. And then dv is sine squared x dx. That means du would be just 5 dx, so nice. And then how do I find v? V is antiderivative of sine squared x dx. No, it's not just cosine squared x. Don't make up weird illegal math. How do we integrate sine squared x or cosine squared x? Remember, we use our identity. So sine squared x is equal to 1/2 times 1 minus cosine 2x dx. You have to memorize this if you haven't already. That's the only way to integrate sine squared x. Okay, so now to get v, I anti-differentiate this expression right here. The 1/2, just leave it outside. It's minding its own business. Don't cause problems, please. Antiderivative of 1 would be, yes, just x. Very good. Antiderivative of cosine 2x, and it's negative. So derivative of sine x is cosine x, so it has to be a negative. Stay negative. And put a 1/2, yes? Okay, now check. Did we just make life better or worse? You know, shall we continue, or did I set things up poorly? Check what you're going to end up integrating. I'm going to end up integrating v du. How do we like it? Oh, I love it because now there's just a 5, not an x. And then I can integrate each of these guys. No big deal. So we're on the right track, okay? Always do those common sense checks. All right, so we're going to have uv minus v du. Let's set her up. U times v. How shall we write it? Put the constants together. There's a 5 and a 1/2. That's 5 halves, is it not? X times x minus 1/2 sine 2x. Okay, cool. Minus v du. I'm going to do the same thing. I'm going to put the 5 halves outside. Integral x minus 1/2 sine 2x dx. All right, looks good. Here we go. We can start distributing, right? This 5 halves x, why not? So 5 halves x squared minus 5/4 sine 2x minus 5 halves. We're ready to integrate this sucker. So antiderivative of x, 1/2 x squared. Antiderivative of negative 1/2 sine 2x. Okay, derivative of cosine 2x would be a negative 2 sine 2x. Remember the chain rule. But there's no 2 in the front, so we have to divide and keep that negative 1/2. So it's going to be positive 1/4 cosine 2x, and then we've got a plus c. All right. Good. Okay, from here, it's just a matter of cleaning it up a little bit more. So let's distribute this negative 5 halves through. So we have 5 halves x squared minus 5/4 sine 2x minus 5/4 x squared minus 5/8 cosine 2x plus c. And then notice I have like terms, 5 halves x squared and negative 5/4 x squared. That's going to give me 5/4 x squared. So final answer, 5/4 x squared minus 5/4 sine 2x minus 5/8 cosine 2x plus c. Nice, nice. Was that your favorite so far? I got one more for you, and this is a definite integral. That way we can practice playing around with limits of integration, okay? Example 5, integral from 0 to pi e to the cosine theta times sine 2 theta d theta. Okay, so I mean, it looks like something that we would use integration by parts for because we've got some sort of product going on, but it's a bit of a mess. And I kind of want to make a little bit of a change of variables first to clean it up before I use integration by parts, okay? And one thing I'm thinking, okay, derivative of cosine theta, say I were to let that be a new variable like t. I'm trying to save u and v for later, guys. Got it? Okay. So say I let cosine theta be t. dt would be negative sine theta, right? d theta. And I don't have that. I have sine 2 theta, not sine theta. But we can fix it because I remember my double angle identities, don't you? Sine 2 theta is 2 sine theta cosine theta. Ooh, okay. So now we have, let's rewrite the original, 0 to pi, e to the cosine theta, 2 sine theta cosine theta, d theta. All right, cool. Here's my sine 2 theta. So let's say I let t equal cosine theta, then dt would be negative sine theta d theta. I have that, sine theta d theta. So negative dt would be sine theta d theta. What about this extra cosine theta? Not a problem. That's just going to be t. Do you see how that's going to work? Yes, love it. So let's rewrite the integral now using t. I'm going to put this negative outside where it belongs. We're going to have e to the t times, just leave the 2 there for a hot second, 2 Cosine theta is t, and then I have a dt. All right, and then you must immediately change your limits of integration so that they are in terms of t as well. You can't leave it as an indefinite integral. No. So t is equal to cosine theta. T of 0, my lower limit, is going to be equal to cosine of 0, which is 1. And then let's change the upper limit. So t of pi would be cosine of pi, which is -1. Okay, so lower limit 1, upper limit -1. Anything you notice we can do to clean things up? Yeah, remember we can flip or switch the limits of integration, and that changes the sign of our integral. So I can rewrite it without the negative sign now, going from -1 to 1. And then while we're at it, please put that pesky 2 outside. So we just have e to the t times t dt. All right, nice. So pretend now this is like a brand new problem, okay? And then from here, we're going to apply integration by parts. All right, good. So we're going to pick u, and we're going to pick dv. Aren't you so glad I saved u for this moment? Yes, we all are. How to pick it? Well, I have t to the first and e to the t. Always going to let u equal t in such a scenario, and then dv would be e to the t dt. If you try it the other way around, it's just going to make the integral worse. If u was e to the t, du would be e to the t dt. But if dv was t, then you'd have like a 1/2 t squared here, and then that's no good. Okay, plus LIPET. Just think of that. Okay, du is going to be 1 dt. And what would v be? Yes, just e to the t. Okay. Did things get better? Why, yes. This is all we're going to integrate. How nice. So here we go. Keep that 2 outside. Bracket. uv is here. T times e to the t. Make sure you show we have to evaluate that from -1 to 1. Don't skip writing that, otherwise it's wrong. Minus integral from -1 to 1 of v du, which is e to the t dt. Okay, good. Now we can go ahead and anti-differentiate. So 2 times t e to the t. I'm going to put the limits at the very end for everybody, okay? So I'm not going to put the straight line right here. Minus antiderivative of e to the t is e to the t, and then this all gets evaluated from -1 to 1. Now remember, we changed our original variable. It was with thetas. We changed it to t, but I also changed my limits of integration, so we don't need to go back to the original variable. We can just evaluate things as they are. All right, so we've got 2 times. I'm going to substitute in 1 now. 1 times e to the first minus e to the first minus, -1 times e to the negative first minus e to the negative first. This is fun. Okay. 2 times, this is just e minus e. Oh my goodness. So that's just 0. And then this is going to be plus 1 over e, right? Plus another 1 over e. So that's 2. What an ugly looking 2. Come on, we can do better. 2 times 2 over e, which is 4 over e. Voila. All right. That's it. That's the last example I have for you. If there's other spicy ones you want me to do, let me know. And I will link the rest of my Calculus 2 video lectures playlist here if you haven't checked it out already. I also have video lectures all the way from Trig, Precalc, Calc 1, Calc 2, Calc 3, working on differential equations and other stuff too. So stay tuned, give this video a thumbs up if you found it helpful, and share it with others. And I have more uploads coming your way, so make sure you subscribe.